Hello ladies and gentlemen, welcome back to what is going to be the 10th lecture for GGS300, and you'll be glad to know that this week it's going to be a fairly short lecture, and then in the lab we're just going to go over a couple of very simple tests, so it won't be too arduous on you, but I will be starting to kind of progress us to wrapping up this part of the course now, because obviously we're at the second part of, the second third part of the actual course. So we'll be kind of wrapping up those more basic inferential tests. So essentially we will have the second midterm, which will be coming next week. And in the meantime, there'll be an assignment this week for you to complete. And there'll also be a whole set of ungraded tests, which, like last time, basically, I'm going to be setting you so that you can get to grips with the material, understand what you do or you don't know, and by taking those tests, it's really going to put you in a good stead in order to actually excel when it comes to the midterm. And I'm really excited for how you're going to do this time round, because some of you did very well last time, and I think the feedback I've been getting is that you've been enjoying the course, which is great. So please do reach out to me if you've got any further questions about how this is all going to go. Last time we did the midterm, I think one of you did say that it was unfair that I'd set work in the midterm week, and that wasn't actually correct. What I actually did was I gave you an extension for the previous week's work submission, so I didn't think that was necessarily that fair, but I just wanted to emphasize that point, that you basically have the whole week in order for you to complete the midterm. There won't be any work there. If there's a work that's done, then that's obviously because there's been an extension from the previous week, which is your own choice as to when you submit or not. Okay. Great, well, look, let's get stuck into the material now, and reach out to me if you've got any further questions that you want to raise. As I said, today we're just going to be going over some relatively simple tests. There's only two of them, so we're looking at analysis of variance across multi-samples, but each one of them is maybe more intricate than what we've been doing in the previous examples. So for example, there might be up to 3 or 4 or 5 steps in one of them. But it's a great test, so hopefully you'll get to grips with what we're going to be doing here, and then we can run over it in the laboratory so that you kind of get a feel for how you move from the theory and the high-level part that we're doing here into actually kind of tapping it out in some code in R and actually getting the test statistic and evaluating what that means. So we've obviously covered in the second part of the course the more kind of advanced inferential tests over here, where we're actually able to evaluate formally hypotheses and make statements about how the world works based on some rigorous statistics which we carry out. And that's a great set of techniques for you to have basically as you start to progress with your own research, your own career after Mason. So I think this will put you in really good stead. As we then move into that final third of the course, what we're going to be doing is focusing more again in this area, but we're going to be going to some more advanced tests. Okay, so that's due to start in 2 weeks' time. So what we're going to do today is focus on analysis of variance, which sounds really scary, but it's just basically thinking through, it's basically just a set of tests that allow us to address multiple samples when we've got more than just 2, okay? So you remember in this flowchart where we started with the different types of data. So we have continuous very often. We're interested in differences and means, and we've been over last week what happens when you have 2 groups. So we covered the t-test and the Mann-Whitney U and the Wilcoxon rank sum tests. And basically this week what we're doing is we're going over those tests where we have more than those limited number. So we can, if we're focusing on parametric data, we can use the analysis of variance. Or if we've got non-parametric data, then we'll be going to be focusing on the Kruskal-Wallis test, which is actually just a bit of it's a small difference to the Wilcoxon rank sums test. It's kind of similar, so it's not going to be too daunting for you, thankfully. So let's get stuck in. So far we've talked about 2 sample tests, that's fine, but very often in the spatial sciences we will have many different samples. Okay, so imagine I told you I wanted you to go out into, I want you to go out to the eastern shore, and I wanted you to take water samples, and I wanted you to take those water samples from a range of different places across different rivers. And then basically, if you had, say, like 5 different types of ecosystem that you wanted to collect those samples from, and then you wanted to test them here, this would be kind of the appropriate test for you to basically use. Okay, so you could look at differences by region with this test across the US, by continent, by state, or as I just mentioned in the example I gave you, by parks or forests, land cover areas, or other regions. So it's reasonably good if you've got spatial data, because you know that might be there might be things going on, which means that different places are not the same as other places, and you need a way to try and formalize and capture that. So the logic of this test is very important. I'm just going to run through it quickly before we get into the actual math. And basically, if the samples that we have are taken from the same population, then the theory is that the means won't differ. Okay, so if I told you to go out and I told you to sample house prices from a particular area, if it's all from the same population, then there shouldn't be any differences between those samples that you collect. Okay, we should get relatively similar means across them. But if the sample means differ by more than the variability which we would randomly expect to happen from ordinary sampling, then we can reasonably conclude that samples have been drawn from at least 2 different populations. Okay, so this is really key. When you're tested on ANOVA, understanding this logic is going to be really important. So you need to know that what we're testing here is whether at least whether the samples have come from at least 2 different populations. Okay, and that's kind of the key way to think about this. It doesn't say that one is from one population and one is from another. It just merely says that something different is happening here, and they're basically coming from different populations. So those 2 tests which I mentioned, they're inferential. The first one is the analysis of variance. So basically that's for parametric data analysis, where we've got interval ratio data. And then we have the Kruskal-Wallis test, which is our non-parametric variant requiring ordinal data. So you remember that that's categories which are basically ordered in some sort of meaningful way. So you remember ordinal and order has a very similar semantic meaning. And basically we're able to use this in those cases, for example, where our data isn't able to meet those parametric assumptions, such as the data being normally distributed with equal variance. Okay. There are differences, though, with the other tests. So, for example, with both ANOVA and the Kruskal-Wallis, the test statistic is always positive, which basically means that we can't use those distributions that we've used in the previous examples, okay? Because if we think about the Z distribution or the T distribution, they aren't useful here because they can be negative, okay? Because if you're thinking about the number of standard deviations around the mean. In this case, as a consequence, for ANOVA, the analysis of variance test, we're going to be using the F statistic, and the F stat is basically the T distribution squared, okay? So we're going to be using something slightly different this time round. And then, moreover, the Kruskal-Wallis test actually uses the H statistic, which is a chi-squared distribution. So we've mentioned chi-squared before in the labs. And we'll actually be covering it again more so when we go into categorical data analysis in one of the lectures next week. But essentially, this is the normal distribution squared, and therefore both of these statistics that we're using here for these tests are always positive, okay? So be aware that the logic, as I mentioned before, is that these tests are basically just trying to show that the samples don't come from the same population, okay? And that's kind of the logic that we have. So we're testing whether at least one sample comes from a different population. The tests don't tell you how many samples are different. They don't give you any indication as to which populations they're from. They just give you this very specific understanding about the source of the data from different populations. Okay, so hopefully these limitations will become more clear as we progress through the lecture today. So you'll remember that we covered box plots in quite a bit of detail in some of the lab work earlier on in the course, earlier in the semester. So essentially, we have this other variant that I'm now introducing. So this is the notched box plot. Okay, so you can see an example over here. We have different regions in the US, and we have high school graduation rates here. And basically, if we use a notched box plot, you can see where we have the mean here. And we have little overlap between the different groups. So this is basically starting to be indicative that these are coming from different populations, okay? So the notches represent roughly a 95% confidence level on the median of a box plot. Okay, that's fine. So it's kind of useful as a descriptive understanding, a descriptive visualization before we begin. I mean, that's fairly standard. We covered this in the previous work, which is that you always want to do some basic visualizations, plot your correlations, and things like this before you start to get into more complex tests. And we'll do more of that as we get through the semester. I think that this is just a nice way for us to think about the variance across different groups. Okay. So let's get into the analysis of variance. We have these 3 different steps, which I'm going to take you through, and we have these different parts within each one of those steps. So this is going to be more complex than the other tests that we've been running through, but it's only one test that you have to learn today for parametric distributions, so it should be easier. Essentially what we're doing first is we're looking at the between group variability, and I'll explain what that means shortly. We have to go through these different steps for calculating that. And then we look at the within group variability. So that's quite similar to what we've been looking at before. So when we get a sample, there's variation among those sample data points, and that's what we mean by within group variability. And I'll explain this graphically as we get through this lecture. And then finally, we basically develop the F stat, so we can get the test statistic for this particular test. So we have some requirements in order for us to meet the analysis of variance assumptions. Obviously, we've already covered that we're comparing the means of 3 or more independent random samples. That's fair enough. That should be fairly straightforward at this point. Those samples are independent, and each population is normally distributed because this is the parametric test, and we're expecting that those populations have equal variance, okay, and that we're using interval and ratio sample data. So if we don't meet any of these assumptions, then we need to think about the Kruskal-Wallis test that we'll cover in the second part of this lecture. So what's the hypothesis? Well, for the H0, so the null hypothesis, obviously here we're saying if they're all from the same population, then that means that the means of those samples will be equal across sample 1, sample 2, sample 3, sample 4, so on and so forth, all the way through to, so K is the number of groups that we're using here to just represent the fact that you can have, if you want, infinite number of groups. So as a consequence, remember K will be used throughout this to represent those different groups. Let's just assume that we have 3 at first because that's the smallest number we can use here, and it's the easiest therefore to understand. For the alternative hypothesis, what we're basically saying, if they're drawn from different populations, is that we would expect that the mean of the first sample, mu1, does not equal the mean of the second sample, mu2, and so on and so forth, all the way through the different sample groups that we have, okay? As I've already mentioned, the test statistic in this particular case is going to be the F statistic. And the way that we get that, essentially, the F is just by working out the numerator here, which is the between group variability. So you'll notice it says B here for the between group. And then the MSW as the denominator. So this is the within group variability. Okay, so we just need to get the numerator here, MSB, and divide it by the denominator, MSW. Okay, and that gives us our F statistic. So all we really need to do is find these 2 terms, MSB and MSW. And the third part of our test, calculate the test statistic, is just this simple division here. So it's really not that complicated. Before we get there, though, let me just go over some theory so that you can kind of understand this graphically. So first of all, the sample is what we call a group here. So let's imagine that we've got 3 samples. That means we've got 3 groups. And basically, we need to calculate the within group variability. So this is the total of all of the sample variances, okay, within a single group. So we also need to calculate the between group variability. So this is the difference between the sample means. So imagine we've got those 3 groups and we're interested in the mean for those 3 groups, or that would be the difference between them here when we're thinking about the between group variability. So if the samples are drawn from the same population, then the between group variability should be very small, okay? But if the between group variability is very large, then we would expect that essentially these have been drawn from a different population, okay? So this is a good example of the null hypothesis where the first sample, the second sample, the third sample all overlap. There's no difference between the mean, mu, and this is where there's no difference. So they're all drawn from the same population, okay? In the alternative hypothesis, this would be where we essentially would expect that those three samples, so mu1, mu2, mu3, all come from different populations, so they have very different means. Okay, so you can see the difference. They're not overlapping here. Here they're all overlapping. Here the means are very far separated from each other, which means that they're most likely very different. Okay, so these are our hypotheses, null hypothesis and the alternative hypothesis. But then actually in reality, case one here just gives us an example of this is probably, this small variation here is probably within the random sampling error that we would expect, and therefore this small difference would probably imply that we don't have enough of a difference between our means for us to say that they come from different populations. So we would probably retain the null hypothesis, so we don't reject the null hypothesis because we don't have enough information. And that contrasts with this example here, case 2, where we've got really quite large differences between the means of those different samples. Okay, so let's say you go out and you collect house price information from Fairfax City, Arlington, and then Shenandoah. And essentially by the time you actually plot the house prices, you probably would get something reasonably similar between Arlington and Fairfax, and then you'll probably get a much lower average house price for Shenandoah because the real estate is just so much cheaper there. So as a consequence, in that case, you would probably reject the null hypothesis because you'd expect that they just came from different populations altogether, okay? Great. Hopefully that's helped you understand this graphically, and if not, then you can read more about this in the book or watch the video again. How do we calculate this? Well, to get the between group variability, essentially what we need to do is to calculate the total weighted mean of all the samples. So we need this x bar t here, okay? So essentially what we're going to do is we need to take the sum of the number of observations in the sample multiplied by the mean of the sample to get the numerator. And then we need to divide it by the total number of observations in all the samples. So say, okay, so this capital N is for all of the samples. So that gives us this x bar t here, the total weighted mean. And then what we need to do is we need to, in part 2, actually get the between group sum of squares. So don't worry if this looks super scary. We'll do this in the actual lab session. We'll work it out by hand. It's not too complicated. So what we're doing to get this is we're basically multiplying the ni by each of the sum of the squares. So basically we end up with this SSB. So this is the sum of the squares for the between group variation, okay? And then essentially, finally, what we do is we calculate the between group mean squares. So we need to take the SSB that we just calculated here as the numerator, and we divide it by the number of degrees of freedom for the between groups. And we get the MSB term that we would like to obtain, okay? So just think of the between group variability as the difference between the samples. And I think the thing I haven't mentioned here, I have, K is the number of groups, okay? So in this case, because we're focusing on 3 samples, that means that we've got 3 groups, okay? So it's relatively easy to get this statistic, and that's the first step in the ANOVA. And the second step, which is just 2 more parts, is as follows. And then finally, we can then reach that third step where we can get the F statistic. So in the second step, what we need to do is calculate the within group variability. So this is very similar to all those other tests that we've done. So if you imagine that I tell you to go out and collect data on house prices in Fairfax, you're going to come back to me and we're going to have probably a normally shaped distribution. And we're probably going to have variation around that mean, but the mean is going to be in the middle of that distribution. And that's essentially what we're trying to capture here, the variation in each of the samples. So we need to calculate this first, the within group sum of squares, so SSW. And basically we need the sum of the ni minus 1 multiplied by the variance, okay, for all groups. And then essentially what we get when we move into part 2 is we need to obtain this MSW term. So we need to take the SSW here, the within group sum of squares, as the numerator, and we need to divide it by the number of degrees of freedom that we have, okay? And the way that we do that here is we need to take the number of groups that we've got and the total number of samples across all of the groups and subtract them. So if we had 100 samples points, we had 100 data points across 3 groups. Okay, let's say that we have 99, so that it's nicely divisible by 3. Let's say that we have 99 data points and we have 3 groups, so we have 33 points in each. And then essentially what we would get is 99 for the n here, for all of the data points that we've got, and then we need to subtract the 3. So we'd end up with 96 as a consequence of the number of degrees of freedom in the sample, okay? And then we need to just divide the SSW by the number of degrees of freedom that we got here. So that's fairly straightforward. I don't think that that's too grueling for you. And once we get to this point here, we're able to get that F statistic and evaluate it in a normal way using a p-value, for example. So we get an ANOVA table as a consequence. So just think of these rows as the between group variability, the within group variability, and then the total variability. And we can then think of the sum of squares that we've obtained, the number of degrees of freedom that we've worked out, the mean of the squares, the F ratio, and then the final p-value, okay? So we can do this, for example, thinking about high school graduation rates based on the regions across the US. So imagine these are by state, and then we've got the region here, and then essentially we would get an ANOVA table as an output. So when we assess the number of regions, we get, say we've got 3 samples, so we've got 3 degrees of freedom. We basically get a sum of squares value, we get the mean squares, and then importantly we get the F value, so the F statistic. But you'll notice here that the p-value is really, really, really small, so it's 1.3 to the minus 12. So this is highly, highly significant. And as a consequence, you know that at least one of these samples has come from a different population, okay? And I think I'll just point out to you before we get into this in R that these 3 asterisks here, they are indicative of whether a result is significant. So if it's a very large number and it's nowhere near the significance level, you don't get anything. If it's quite close to the significance level, you'll get a full stop, like just here. And then if you are below the 0.05 significance level that's fairly standard, you'll get 1 asterisk, and then as you get lower and lower and lower, you get more asterisks, okay? So as a consequence here, because we're below the 0.001 significance level is really, really, really small, really low, we get all 3 of these asterisks. So it just means that as you look at a large table, obviously this is quite small, it's quite easy to interpret. If you had a regression table and you were running 20 different models and they've each got 10 variables, then this basically makes it easy for you to skim across the whole regression results table and kind of find the important results really quickly. And then it's kind of easier on the eyes. Okay, great. Let's move on now to the Kruskal-Wallis test, which should be relatively straightforward for you. Okay, it's another big scary equation, but it's not actually that complicated. In fact, it's very similar to the work that we did last week, okay? So here what we're doing is we're comparing the mean ranks of 3 or more independent random samples for differences, okay? The important thing here is this isn't the arithmetic mean, this is the mean ranks. We're ranking these results like we got last time, like we did last time in the lab last week for the Mann-Whitney U test. So essentially what we need to do here is we need to meet the assumptions that we have in order to actually fulfill these tests. So we need 3 or more random samples, fine, the samples need to be independent, okay, we come into this issue every week. The populations can be non-parametric distributions, and ultimately we expect in this case ordinal data values. Okay, so that's one reason why we're ranking these. And we could use interval or ratio data maybe if we tried to use ANOVA, but we didn't meet that parametric assumption of having a normally distributed set of data, then we could downgrade it so that we had ordinal data. Okay, so we just had an understanding of the ranking of those observation of values. It's actually very similar in terms of the hypotheses. So the null hypothesis is where basically the samples all come from the same population, they're identical. Whereas the alternative hypothesis essentially is where the populations are that they're not identical. Okay, so we expect the samples to have been drawn from different populations. Obviously, we're using the H statistic here for a number of reasons. Number one, this is the Kruskal-Wallis test. It uses the H statistic. Number two, we're using the H statistic because we need the positive statistic. We can't have a negative one here. So that's the reason for that. And then essentially on the right hand side here, what we have is we need to basically find the H statistic. So essentially we need to take 12 as the numerator here and then divide it by the total number of observations that we have multiplied by the number of observations plus 1 multiplied by, and then we need to find for all of the samples we need to find the R squared value here. So it's the squared value of the sum of the ranks. Divided by the NI number, so the total number of observations in the sample, multiplied by -3 times by the number of observations we have plus 1, okay? So we're going to go through this when we get into the laboratory. I'm not going to go into too much detail about this equation here, but if you need a correction factor because we've got ties, then you can add this numerator on, and it makes it even more difficult, but not to worry. The important thing about these equations is that you just break them down into steps and you address them really easily, doing one little bit at a time, and then that's kind of the nice way to kind of address this. So what are the steps for actually carrying out the Kruskal-Wallis test by hand? Well, we basically need to get all of the observations from all of the K samples that we've got. So imagine we've got these 3 samples where I told you to go out and get house prices from Fairfax, Arlington and Shenandoah. And we combine them all into a single list, just like we did last week in the lab work. So a very similar approach to the Wilcoxon test. Sorry, that's right, it was the Wilcoxon test we did last week, not the Mann-Whitney test. So essentially then when we've got all of those observations linked, so sorted in a list, we then just need to rank them, okay? So we need to put a number against each one of the rows based on where it is in the distribution, so the ordinal distribution. And then essentially what we do is we have to deal with the ties. So there may be some where we've got the same value and that means that they're tied for a particular rank, in which case we need to allocate the average rank between those. And then the ranks need to be summed, okay, so that's how we get the sum of the ranks in order to calculate the H value, and then it's quite simple from there. We can just use a standard p-value to evaluate that H statistic, and we can do that in R just by using the p-chi-squared function. So you should be fairly used to now using these functions in order to obtain probability values in order for us to get the p-value. Okay. So the Kruskal-Wallis test is an extension of the Wilcoxon test. Remember, it's non-parametric. Great, so that means that the actual ranks that we're getting are the mean of the ranks. It's not the arithmetic mean, so it's not continuous data. We would expect, as stated in the null hypothesis, that each group has roughly the same average rank. That's fine. Whereas obviously if we're getting very significantly different average ranks, then that would be indicative of them coming from a different population, okay? And so that would be an example. If there were patterns like we had in the previous example, the null would obviously then be rejected. And the notch box plot, as I showed you previously, is a kind of good way to start thinking about visualizing those different groups if we have to so that we have some sort of a priori understanding before we move into actually running the tests, okay? So it gives us some indicative insight. And we end up with this type of result when we do run the Kruskal-Wallis test in R. So imagine we were running it for that high school graduation data by region for each state, and essentially we get a chi-squared test statistic of 36.1524. We've got 3 degrees of freedom here because we've got 3 regions. and we end up with a very, very significant p-value in this case. So 6.9 to the -8, so it's definitely a significant result, well below the 0.05 level that we're looking for, the significance level, so that we can be at least 95% sure that the results haven't just occurred by random. Okay. So this has been an incredibly short week. I hope that you've enjoyed the shorter lecture. Obviously, we're still going to run through that information in the lab session, so that you kind of get an idea for how we tap this out manually. This is the end of the second unit of the course now, so I will cover next week categorical tests in one of the lectures, but the main thing is that you need to basically complete the assignment that I've set, which will be due next week, and then next week, the following week, you'll have the actual tests, which are ungraded, and then you'll basically have a week for you to actually complete the midterm exam. Okay. Great, well, that's it from me for today. So it's been nice to see you all again, and good luck with the exam preparation, and don't hesitate to reach out to me if you've got any further questions. Okay, thank you very much. Goodbye.